Greetings everyone. Today I'm going to do an oral presentation for Fellowship.AI's Ancients Challenge. The topic's about computer vision, using a pre-trained ResNet 50 for training on the data-powered dataset by Maria and Andrew. This type of problem falls into the category of fine-tuning for downstream class usage, a pretty simple one, as I thought so a few days earlier. So now, let's dive right into it. First, I've got an introduction to make. My name is Minhu, currently a sophomore, majors in artificial intelligence, a bachelor at Vietnam University, Ho Chi Minh City, the University of Science, currently ranking at 900 worldwide, according to Pure World University. I've been participating in multiple hackathons on AI development and constantly surrounding myself with rigorous knowledge within the view. As a result, it leads me to the state of where I am now, applying for a fellowship position at Fellowship.AI, as I think this opportunity would be an excellent choice for my pursuit in AI. It is not just about the content and knowledge in this fellowship that does matter to me, but also the chance to be part of a dynamic network of AI practitioners. For those who are interested in learning more about my background, additional information is available in the description. Now, without any further ado, I shall begin my presentation. Okay, so this project was done on Google's platform using double T4 GPU accelerator. The first step, obviously, you have to download and extract the dataset file from here. Let us begin by examining the dataset characteristic and the challenges they presented. Through exploratory data analysis, I identified three significant challenges. First one is data imbalance. As you can see here, the minimum samples in your category is 40, while the max samples is above 200. And there's also the problem with limited training data from the original paper. You can see the training and the validation only accounts for 25% of the whole dataset. The last one is about the image dimension distribution. As the image has a lot of variation between from 500 to 1000 in pixel. Okay, so which insight have I concluded from this data analysis? There's class imbalance issues, and this imbalance could lead to biased model performance toward majority classes. And the second one is data splits, and this limited data training is difficult for a model to learn class-specific features. And the last one, I don't think it does matter real much though, because all the pipeline nowadays have a built-in pre-processing for image. That's the image dimension variation. Alright, so now to address the problem of imbalanced data, I have developed a three-phase approach inspired by the recent advance in self-supervised learning. Those are SimCLR, a simple framework for contrastive learning of visual representation from Google Research. This paper introduced the fundamental concepts of contrastive learning with data augmentation, demonstrated the importance of strong augmentation for self-supervised learning. The second one is MoCo, Momentum Contrast for Unsupervised Visual Representation Learning. AI research. This paper introduced the mechanism. So to effectively negative samples. And the final one is BYOL. Bootstrap your own Latent, a new approach to self-supervised learning. This paper, though, demonstrates contrastive learning without negative pairs, and it used two networks, both online and targeted, for momentum updates. And okay, so these are the libraries that I use to implement for my solution, including PyTorch, as the framework builder, and other plotting visualization library. About the second problem, the dataset split concerns I pre-order the dataset using a random split with a zip equal 42 and the ratio of train validation and test respectively equal to 60%, 20% and 20%. Okay, now it's time to have a look at the proposed pipeline. There's 3 phases in total. And first step, we need to obtain pre-trained ResNet 50 from Thought Vision API and put it into the first phase, self-supervised pre-training. In this phase, we implement contrastive learning for robust representation learning. Emphasize strong augmentation pipeline, which include generating positive pair using strong augmentation, like random cropping, color jittering, rotation, or cutout. And finally, to end this phase, we train it with contrastive plot to obtain a self-supervised pre-trained model. And to the second phase, though, is supervised fine-tuning. So that we use learn representation for classification to implement it class-aware contrastive loss to address imbalance, and then into the final phase is test time augmentation and generate many multiple augmented view during inference for a more robust and a more reliable results. Now let's see them in action. And so the first thing you need to care about is the augmentation pipeline right here. So this function creates different augmentation strategy for each phase: the pre-training phase, the fine-tuning phase, and the testing phase. Overall, there's some common elements like resize crop, horizontal flip, random rotation, color jittering, or grayscale in each phase. Okay, so now we get to see what is the contrastive mechanics in my pipeline look like. The first one we need to talk about is the contrastive transform. It's a data augmentation class that can create multiple views of the same image. It takes a base transform from pre-train or fine-tuning or testing phase, and then creates an end view different augmented version of each input image. And it also used to create positive pairs for contrastive learning. And the next one is contrastive model. It's the ResNet 50 model, but modified for contrastive learning. And the encoder is its purpose to modify the final layers to output a 128 dimensional features. It has two purposes. It can output feature embeddings when the feature is equal to, and otherwise it can perform classification in the default mode. And the last mechanic I want to talk about is the normalized temperature scale cross entropy loss. This is designed to take encoded feature pairs and create similarity matrix between features. It is also used to generate positive pairs which are augmented views of the same image, or negative pairs is the feature from different images. This also has a temperature scale parameters which control separation sharpness. So in general, the process will look like this. The first step is to normalize feature. Second step is to compute the similarity. The third step is to identify positive and negative pair. And the final one is calculate the loss to maximize similarity between positive pair while also minimizing similarity between negative pairs. And additionally, how all these contrastive mechanics work together is contrastive transform create two views of the image. The contrastive model encodes these views into feature space, and the loss function compares these features to learn meaningful representation. And the learned feature can then be used for downstream tasks like classification that I'll talk about right now. And here I have a trainer class that will be used to execute each phase properly, from the pre-training phase to the training phase and the testing phase. This also has a plot training history that I will use to visualize the training process later. And now it's time to actually train the model. As I have run the experiment beforehand, this is the predetermined results. The final loss I've achieved on trained datasets is about 0.5, and on validation is about 1.0, which is pretty good. I think so. Okay, so now as we come to the final section, the empirical results, then this demonstrates the effectiveness of this approach. As you can see here, the final epoch, the training accuracy stay at around 82%, and the validation accuracy is about 74%. And looking at the plot over the course of 20 epochs, the both loss and accuracy curve show that clear convergence patterns. But there's a growing gap between training and validation accuracies after the epoch ends. The validation loss also stay higher than the training loss and show more fluctuation. This suggests that the model may be a bit mild overfitting, but not severe, since validation metrics continue to improve after that. There's some potential improvement from this. This could benefit from the running rate schedule to stabilize later efforts, and additional regulation might help reducing the training validation gaps. And the last one, maybe longer training might yield marginal improvements as curves don't happen completely plateaued yet. I think this model shows good learning overall, but still has room for more optimization in terms of generalization and stability. And it's time to measure specific metrics on test results to employ whether this model has a decent performance on the test results or not. The metrics I choose to use in this test in analyzing the test results is the precision, sensitivity, and specificity due to the class imbalance. So here they are, and I think these are pretty good results. The precision is just about 78%, and this indicates that where the model predicts flowers belongs to a specific class is correct about 78% of the time. And by being a weighted average, it accounts for class imbalance in the dataset as well. The next metric though is the sensitivity. Um, it shows that the model correctly identify about 75% of the actual flowers in each class, and it indicates that the model the, the ability of the model that can find all instant of each flower type. The final metric is the specificity, which is about 73%, and it means that the model correctly identifies whether a flower does not belong to a class about 73% of the time. And both of these sensitivity and specificity metrics is balanced with each other. So it suggests that the model isn't biased toward any positive or negative prediction. Okay, so now let me show you the fine-tuned model in action. Here we have a few test images that the model hadn't seen during training. Let me choose class 2. Okay, their confidence is pretty high. Notice how the model not only provides classification class, but also confidence score for its prediction. The test time augmentation helps reduce the prediction variance and improve the reliability of the results. Let me just test some more with a few more images for you to see. There we go. The confidence may vary between class, but I think there's still more rooms for optimization and improvements in training this model. Thank you for your attention. I'm looking forward to your response anytime soon. Goodbye and have a good day.